What if Nobel Prize winning science was wrong? And not wrong in a small way, but wrong in a way that changes everything that we think we know about the universe. That's the big argument raging in cosmology right now. So in 1998, two teams of astronomers discovered that the universe isn't just expanding, the expansion is accelerating. Something is pushing it apart faster. That's what won the Nobel Prize back in 2011, and it's become one of the main pillars of our best model of the universe. We call the thing that's causing the accelerated expansion dark energy, and we've since found lots of other pieces of evidence for it, but we still don't really know what it is yet. But recently, a group of cosmologists, Sun and collaborators, have claimed that the supernova data used to make the dark energy discovery has been hiding a bias for 30 years, which when you correct for that bias, switches the acceleration of the universe's expansion rate to a deceleration. Now, like with any scientific paper that poses a big challenge to the widely accepted theory, this has been getting a lot of attention both in the research community and online. However, I want to make it really clear up front here that a lot of cosmologists are not convinced by the evidence that Sun and collaborators have presented, and there have been a lot of rebuttal papers published claiming the bias in the supernova data has already been accounted for, meaning we still conclude the universe is accelerating. But at the heart of this latest scientific discussion is a question that us astrophysicists and cosmologists agree poses a really big problem. Do we actually understand the supernova that we've been using as our cosmic distance measures for the last 30 years? So in this video, we're gonna dive into all of this and chat first about why supernovae aren't perfect standard candles, then chat about the claims of Sun and collaborators that there's an age bias in this supernova data, meaning the universe is actually decelerating, then chat about why most cosmologists aren't convinced just yet, and then finally what the next generation of telescopes need to do to solve this problem. So let's start with the first one on the list there, why supernovae aren't perfect standard candles. So a standard candle being something that has the same brightness wherever it is in the universe. So then from how bright it appears to us here on Earth, we can then use that to work out, okay, well then how far away is that object, with the fainter it is, meaning the further away it is. And the best standard candle we have for long distances is a type of supernova known as a type 1a supernova. So this isn't your classic supernova where a star runs out of fuel and explodes. That's what's known as a type 2 supernova. A type 1a is when you have two stars orbiting each other and one of them has already run out of fuel and fizzled out to become a dense white dwarf star. Basically, it's the leftover core from a star like the sun, but there's no nuclear fusion going on in that white dwarf star anymore. So the only thing that's actually resisting the crush of gravity inwards and stopping it collapsing down is electrons. The electrons that usually are, in orbit around the centers of atoms, they've been freed, but they're now packed as tightly as they can go, and that's what's resisting gravity. But there's a limit to what electrons can resist at around about 1.4 times heavier than the sun. So if a white dwarf starts to steal material off the star that it's orbiting so that it grows ever heavier, when it reaches that 1.4 times heavier than the sun is when gravity wins out against the electrons and you get a collapse inwards, causing a supernova, which always releases the same amount of energy because E equals mc squared. Energy and mass are basically the same thing. And so the supernova is a standard candle. It always goes off with the same brightness wherever you are in the universe. Except that it doesn't. Because if there are more heavy elements in the white dwarf to start with, then those heavy elements are more opaque to light and so the supernova is dimmer. Or if in the nuclear fusion that occurs during the supernova more radioactive nickel is made, then that will produce a brighter supernova. So there are a few things that we know cause some variation in the brightness, and we can observe that and correct for it and normalize them back to a standard brightness. The first is how long it takes the light to fade. So with all supernova, we observe what's known as a light curve, basically the brightness over time. So after a supernova explodes, it reaches peak brightness and then starts to fade slowly over time. Whereas the ones that make more nickel peak more slowly and brighter, but then fade more slowly as well. So measuring how long it takes to peak and fade tells us how much brighter than the standard the supernova is, and then we can correct for that using something known as the trip formula. Without that correction, the distances that we then measure for those supernova wouldn't be quite right. That means the distance we then measure for the galaxies those supernovae are in aren't quite right either. And when we plot that against the speed the galaxy is moving away from us to work out how fast is the universe expanding, we'd introduce a lot of error into that measurement. So that correction was published by Tripp in early 1998, and by late 1998 is when Rees and collaborators published their Nobel Prize winning study, which showed that as you went out to greater distances, supernovae were fainter than expected, suggesting they were further away than expected by about a factor of 10 to 15%. And crucially, this only affected supernovae in more distant galaxies, not all the supernovae that they had observed. That was eventually interpreted as space had expanded more than you would expect from just a constant expansion speed, i.e. the universe was accelerating in its expansion. And that result doesn't stand alone. Measurements of the cosmic microwave background point to this as well, and also the large-scale clustering of galaxies all point towards an accelerating universe. But then, in 2010, another issue with the standard candle nature of supernovae was found. Sullivan and collaborators, and then later Lampeitel and collaborators, showed that even after you make the known corrections to supernovae to make them standard candles, supernovae are still fainter than you'd expect in less massive galaxies. Since then, this has been referred to as the mass step, and it's just been added in as an extra correction to the Tripp formula, but what's actually causing it isn't well understood. Some people think that it could be dust that blocks the light from the supernovae in less massive galaxies. They tend to be spiral galaxies, which we know are very dusty. Or it could be due to the amount of heavy elements in less massive galaxies on average, which we already know affects how bright a supernovae can get. Or it could be due to the age of the star going supernovae. So older galaxies tend to be more massive because it takes that long to build up that mass in stars, whereas less massive galaxies tend to be younger. That's a really well-known correlation of galaxy properties. So does that mean the mass step is actually an age step, and it's all to do with the age of the star going supernovae? That's what was claimed by Rose and collaborators in 2019, and more recently by Chung and collaborators in 2025, who both showed that supernovae in older galaxies are brighter and those in younger galaxies are fainter. But we have to be really careful about what we mean here, because it's not really the age of the galaxy that matters, it's the age of the white dwarf star that went supernovae. We call that progenitor age. And because older galaxies tend to host older star systems on average, galaxy age works as a rough stand-in to see this relationship between supernovae brightness and progenitor star age. Which brings me to part 2. The claims of Sun and collaborators that there's an age bias in the supernova data, meaning the universe is actually decelerating. So the more distant a galaxy is, the longer light takes to travel to us through the universe. So we see them as they were billions of years ago. We are observing galaxies when they are much younger. So Sun and collaborators in 2025 argued that the supernovae that we've observed in galaxies at greater distances are fainter than we think because of this age step bias. They claim that the younger galaxy fainter supernova effect leads to a 0.16 bias in the brightness of the supernovae measured. And that is a statistically significant difference between the brightness that's predicted by our current best model of the universe. And instead, they argue the data supports the idea that dark energy is changing and that the universe is actually decelerating. Now, these models of the universe where the accelerated expansion rate is changing have been coming up a lot lately. The DESI survey, for example, have found evidence for it when looking at the large-scale structure of the universe, which I've covered on my channel before. And the physics term to describe changing acceleration is a jerk. Speed, acceleration, jerk. So you might have also seen me talk about how the universe is jerking on my channel before as well. But the key thing to understand about this, the DESI result, is that they've still claimed that the universe is accelerating. It's just not accelerating as fast as it was. So if you think about this in relation to like in your car, when you've got like the accelerator pedal and the brake pedal, the universe's foot was down more on the accelerator pedal in the past and it's pulled up ever so slightly. It's still accelerating. It's still got its foot on the accelerator pedal, just not as hard, right? The universe hasn't put its foot on the brake yet to start decelerating. But Sun and collaborators claim that DESI only found that because the supernova data had this age bias. So this is the key plot here. On the horizontal axis, you've got the age of the universe, and on the vertical, you've got the rate of acceleration of the universe. Our best current model is shown by the black line, a very clearly accelerating today universe. Then you've got three other lines here, all of which use the DESI large-scale structured data that's, key thing, is independent of the supernova data. The green line shows the original result from the DESI paper, combining your large-scale structure data with your supernova data that, according to Sun, have been uncorrected for this age bias. That gives you an accelerating universe, but one that is doing so at a slower rate now. The blue line is what you get if you don't include any supernova data at all with the large-scale structure information from DESI, whereas the red line is that data combined with Sun and collaborators' supernova corrected for age bias, both of which give a currently decelerating universe. So this seems like a very convincing argument and piece of evidence here, so why then are most cosmologists not yet convinced by this? So there's been quite a few papers published discussing this, including a lot of rebuttals to this argument. I'm going to focus on two main arguments here. Firstly, from Wiseman and collaborators. They point out that Sun and collaborators corrected for this supposed age bias before then also adding the standard mass correction that's usually applied to supernovae. So they're basically correcting for the same thing twice and getting extra faint supernovae as a result of that overcorrection. So Wiseman and collaborators applied the standard mass step correction and then looked at this age bias with distance and showed that the bias had largely disappeared. It had already been absorbed by the standard correction that every modern cosmology study already applies. And the second argument, and the key thing to remember here, is that Sun and collaborators are assuming that the galaxy age is a proxy for the progenitor age, the age of the white dwarf that went supernova. But is that a good assumption? Well, according to Murakami and collaborators, no, it's not. They used a sample of nearly 7,000 galaxies with known supernovae observed in them and modeled the galaxy's star formation histories, trying to pin down, okay, well, what's the most likely star formation burst in this galaxy's history that could have formed the star that eventually turned into a white dwarf and then went supernovae? That can give you the most likely progenitor age, and what they found is that doesn't really correlate nicely with galaxy age at all, with up to 5 billion years difference in some cases. And so Murakami and collaborators show that if you perform all the standard corrections, the trip formula with the mass correction, and then you look at the progenitor ages to see if there is then an age bias left over, it doesn't give you anything beyond what's already captured by the standard mass gap correction. But interestingly, it still agrees with the conclusion from the DESI survey that the acceleration rate is changing and that the acceleration is slowing down. So then that seems like a really clear-cut, convincing argument as well, but there's been rebuttals to those rebuttals and the whole thing is just getting messier and messier. So, what then do the next generation of telescopes need to do to finally solve this problem? Because thankfully we have two telescopes that we're going to be getting data from very soon that should be able to help here. We have the Vera Rubin Observatory in Chile and the soon-to-launch NASA's Nancy Grace Roman Space Telescope. And both Rubin and Roman are set to do what's known as a survey of the sky. This is where you split the sky up into chunks, like a mosaic, and you observe every single chunk and then go back and do it again, and you get a complete picture every few days. And then if anything has changed since the last time you observed it, whether it moved like an asteroid or got brighter like a supernova, we should be able to spot it. Rubin is going to do this every 3 days for 10 years. And Roman is going to do this from space every 5 days for 2 years. And so at the current rates of detection of supernovae, we can then get an estimate for how many each of them will detect over the lifetimes of these surveys. Roman's set to detect around about a few tens of thousands of supernovae, whereas Rubin is set to detect over 1 million supernovae in its 10-year lifetime. To put those numbers into context, the age-brightness relation from Chung and collaborators in 2025 used just 300 galaxies. With more supernovae, you can then sort more finely by things like galaxy age and progenitor age and mass of the galaxy and distance to the galaxy, so that you can understand how all of these properties relate to each other, so that you can do better corrections, better normalizations to the supernovae to make them true standard candles. Plus, Roman should push the detection of supernovae out to much greater distances, taking the record from 8 billion light years away to hopefully as far back as 11.5 billion light years away. And with more supernovae detected at greater distances, you're then more sensitive to any biases that correlate with distance that then affect our ability to figure out, is the universe accelerating in its expansion. Roman is set to launch at the end of August 2026, and we could have first look images by the end of the year, with science surveys starting in early 2027. Supernovae detections then won't be very far behind. Meanwhile, Rubin has already started its survey, and we're getting multiple alerts a night for supernovae detections. Those alerts and the data are made public straight away, so you can even check it out yourself if you want. I'll pop a few links in the video description down below. So while this argument on age biases in supernovae data is far from settled and will continue to rage in the scientific literature, no one is tearing up our best model of the universe just yet. Anyway, and so you can confidently state that based on the current evidence, it appears like the universe is accelerating. But what this debate has done is shine a light on a problem that the whole astrophysics community agrees needs solving, because we still don't fully understand the supernovae that we've been trusting as our cosmic distance rulers for 30 years. But that's okay. That's science in progress. And with Rubin already scanning the sky every few nights and Roman about to launch, we're about to detect so many supernovae in a bunch of different galaxy types across a huge range of distances that the answers to these scientific questions are going to be buried somewhere in that huge deluge of data, and all we have to do is find them. I think that's the roof like expanding in the heat, that little crack, crack, tap, tap, tap thing. Except that's not quite true. Oh my god, I'm sweating so much. Oh, I thought I could do this with my hair down and the window shut. I might just have to open the window and be like, I hope there's just not enough noise that comes out of it, you know? I mean, at least it's not 35 degrees anymore, it's just 25 degrees, but still. Who decided to put a filming studio in the roof? Nope. Nope, 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 nope. Fluid dynamics. Getting a breeze going. Am I making myself hotter in the process? Who knows? But let's use fluid dynamics. Ow, I knew that was coming.